With simple harmonic motion, we would expect a particle to oscillate back and forth theoretically forever, because at any given moment there is going to be a restoring force pulling it back towards the zero displacement position. So if it has a large positive displacement, then there will be a correspondingly large negative force and therefore large negative acceleration pulling it back towards the origin. And similarly, if it's got a large negative displacement, there'll be a correspondingly large positive force and therefore positive acceleration, again pulling it back towards its starting point. But of course, by the time it reaches its origin point, the point of equilibrium, it's been speeding up all the way there, so it's going to be going at its fastest at that moment. And so even though it's not accelerating as it passes through the equilibrium point, it is still moving, it's still got velocity. So it continues until it reaches the point where it's lost so much of its velocity that it reaches zero velocity again, which is the extremes, the maximum or the minimum displacement points, and then it starts moving back the other way. Now, I'm going to talk briefly during this video about the effects of damping. We can have over damping, or sometimes called heavy damping. We can have under damping or light damping, and then there's something called critical damping, which is somewhere in between. We're going to talk about the subtle differences between them, and I'll demonstrate a bit of how you can do this for yourselves, play around with GeoGebra. So you'll notice there's an extra element here, apart from the omega, which represents the angular velocity, which will affect the rate at which the object oscillates. Other than that, there's another term in here, K. K represents the force of, for instance, air resistance, something which might affect the size of the oscillations. So the amplitude, as time goes by, that might change. This is much more realistic when we're considering a real life scenario. If you've got something oscillating, then it's not going to oscillate forever. It's going to gradually reduce the amplitude of its oscillations and settle down towards its equilibrium point as time goes by. Now, the greater the force we have there, the more rapidly it shrinks in amplitude. But all of these examples so far are what's called light damping, because we still have this oscillation going on as time goes by. Now, the K, you will recall, came from a term in the original differential equation, which was, instead of the standard one, which was the second derivative being equal to minus something times x, we had an additional term where, in addition to the basic bit that gives us simple harmonic motion, we also have another force impacting the acceleration. And that additional force comes from air resistance, for instance, which is typically modeled to be proportional to the velocity. And this would be slowing us down in the direction that we're moving. In other words, if you're moving forwards, this force will be acting backwards, and if you're moving backwards, this force will be acting forwards. So unlike the restoring force, which always acts towards the center in terms of displacement, the resistance force will always act in the opposite direction. That's why we've got a negative, the opposite direction to your velocity. Now the velocity is, of course, dx by dt. So we can rewrite this equation as d2x by dt squared plus k dx by dt plus omega squared x equals 0. And we've got a second order homogeneous differential equation. So we can solve it in the usual way. We would use the auxiliary equation to determine the roots of this equation, and just as importantly, to determine what the nature of the roots is. Perhaps we've got two distinct real solutions. Well, in that case, we would expect to see the discriminant being positive. If we look at the discriminant of the auxiliary equation, in this case, because the auxiliary equation is lambda squared plus k lambda plus omega squared. Now remember, lambda is just the arbitrary variable we've made up, you could use m or something if you like, that's the one that the auxiliary equation is based on. So this thing is the auxiliary equation itself. From it we can construct the discriminant, b squared minus 4ac, which is of course, in this case, k squared minus 4 omega squared. And in some cases that's going to give a positive answer, sometimes negative, and sometimes 0. In the case where it's positive, we would expect two real solutions, and they would be, let's say those solutions are alpha and beta, two distinct real solutions, alpha and beta. Then our general solution to the differential equation will be x equals a e to the alpha t plus b e to the beta t. But of course this doesn't have anything to do with sine and cos, it's just exponentials, and that's exactly what we see if we sketch a graph. This is an example where you have a positive discriminant, so we've got heavy damping or over damping, where the system has got so much resistance, it's quite slow to reach the equilibrium point just because it's being slowed down as it moves. So it's not just that we're reducing the wobble, we're actually over damping means we've gone a bit too far. We've made it hard for the object to even reach the equilibrium point, let alone to so we have reduced the wobble, but we've gone a bit overboard by increasing k too far. And if we increase k too far, you can see, particularly compared to omega, if I make omega relatively small here, then if we make the value of k too big, it takes this object a long time to get down to a modest amplitude. You can see if it's allowed to wobble, then potentially it wobbles for a while. If we reduce the wobble by increasing the amount of resistance force, then that wobble reduces. And then we get to a sweet spot somewhere about here, in fact, where k is 2 when omega is 1. You notice that gives us a perfect zero discriminant. Anything beyond that, and we get over damping, where we still get this exponential decay, but you'll notice it's a rather gradual curve. And that's because this object is being slowed down on its way to the equilibrium point. And that's an example that we've got here. So this is called heavy damping or over damping. And that will happen whenever you've got two distinct real solutions. Now, the sweet spot is somewhere in between. We'll come back to critical damping in a moment. The more natural one that you're likely to have seen or come across or thought about is the light damping situation. If the discriminant is negative, we get two complex conjugate roots, sometimes called two non-real complex roots, to emphasize the fact that they must have an imaginary component. And that means that x is going to be modeled by something like e to the pt a cos qt plus b sine qt. In other words, something trigonometric, that's the a cos qt plus b sine qt section, coupled with something exponential, e to the pt. This bit will depend on the real component, and typically what we'd expect to see is exponential decay enveloping some kind of sine wave. And that is the situation we refer to as light damping. So if k is not particularly big, we see this sort of situation here, where as the particle bounces up and down, it does so less and less. So it starts out at 5, dips as low as minus 2.5, back up as high as 1.8, down to 0.4, and so on. Now, if we increase the value of omega, you can see that this gives us a greater frequency. It doesn't actually change the envelope within which the curve rests. This is the same exponential envelope, but it does mean we've got a larger negative discriminant here, which means you'd have to do a lot more to tamp out those oscillations entirely. In fact, with this scale, we can't get high enough. We need omega to be lower in order for this to represent critical damping or over damping. Provided you've got a large enough omega, you're always going to get some oscillations. So that's why it's not just a case of making K large enough, it's also a case of making K large enough relative to omega. If K is 3.1 and omega is 1.5, then we have heavy damping. But if omega is just slightly bigger, then we're back to light damping again. On the other hand, if we keep omega at 1.7 but we reduce K, then now we're at light damping. If we increase K, we're back to heavy damping again. So there's an interplay between the two. And this is the one, like we say, that you're more likely to come across if you've got something like something bouncing on a spring and you're observing it wobble up and down, but the oscillation is getting gradually less and less severe as time goes by. But it's still got this trigonometric term in it. The interesting one, and the reason why the other two sound like they're not the best, over damping and under damping both sound like they're not optimal. That's because critical damping is the optimal one. So depending on what you want, usually this is the optimal solution. What we find here is that the discriminant is exactly 0. So it's a sweet spot we're looking for. We're trying to get K to be basically twice the size of omega. If K squared minus 4 omega squared is exactly 0, then we're looking at a value of K which is twice the size of the value of omega. And if that happens, then we slow the thing down enough that it doesn't wobble, but not so much that it takes ages to reach its equilibrium point. And that's what's clever about this. And this is why typically this is what engineers are attempting to do. So for instance, if we've got an omega value of 2, then we get heavy damping for any value of K above 4. And as we reduce the value of K, you can see how this exponential curve is becoming better at dragging down towards the equilibrium point. If we drop it too far, then it's going to go below the equilibrium point and wobble. And even though you can't quite see it, technically it's wobbling back and forth just less and less forever as time goes by, with smaller and smaller amplitude to be sure, but it's still wobbling. However, if we can get K equal to the sweet spot exactly twice the size of omega at 4, we get critical damping. This reduces the amplitude as quickly as possible to the equilibrium position, but it doesn't reduce it so quickly that it overshoots on the other side. So this will shoot down towards the 0 mark and then get closer and closer to it without going beyond it. And this is why it's the sweet spot that engineers are usually looking for. In this case, when the discriminant is 0, what we get is a repeated real root. So our solution looks something like this: a plus bx e to the power of alpha t. Oops. A plus bt e to the alpha t. This is x in terms of t, not y in terms of x. So in general, we see this effect with light damping. We can actually look at a couple of special cases. So this is what happens if K is 0. When K equals 0, we're looking at a different situation really to the damping entirely. It still calls it light damping here, but technically there's no damping at all. We still get the oscillation, but when K is 0, this reduces to the normal simple harmonic motion that we've seen before. So we're not getting any kind of exponential decay whatsoever. But you can go further than that. You can change the value of K to be a negative. So what does it mean for K to be a negative? If K is less than 0, this suggests a force in the direction of the velocity. That's not what friction does. It's not what air resistance does. Things don't make stuff move faster in the direction it's going. They make it move slower in the direction it's going. But we could have some kind of external force doing this. When you have a clock running its pendulum, effectively the clock is not trying to force greater and greater oscillations. What it's trying to do is mitigate the effect of the damped oscillation that friction will give. So it just gives enough of a kick to keep the oscillation going to counteract the effect of friction. You can do more than that. You could actively force the oscillations to become bigger instead of reducing them. And this is why this is called forced oscillations, or forced oscillation. And it's exactly the same mathematics. All you need to do is change your K value. So instead of being small or 0, you make it negative. And suddenly you just get the reflected version. You can look to the left. As time becomes negative, it looks like damped oscillation. But to the right, we're just getting greater and greater values. This thing is shooting off higher and higher, lower and lower every time. So even if we were to zoom out a bit, you can see the effect of this. Now, K doesn't need to be particularly large in size, but if it is negative at all, then eventually this is going to give you some crazy results. This is what happens when you have soldiers marching in step across a bridge. The frequency of the marching soldiers, if it's close enough to the resonant frequency of the bridge that they're marching across, can have the effect of making the bridge swing more and more. And there have been cases where bridges have collapsed because of the regular tread of soldiers walking across it. This is why these days, if soldiers go across a bridge, the usual approach is to recommend that they break step as they walk across the bridge. So they're not walking all left, right. Then at least that way, although there will be similar frequencies, the peaks and troughs will be all over the place, and you're less likely to pick up this resonance and have the oscillations get bigger and bigger and blow out of control.